Thank you all for coming. I'm so glad to be here and get a chance to tell you about the work we're doing at Boston Dynamics in building robots. It's really work that's kind of the love of my life. It's so much fun building machines, especially when we come up with one that does something a little different than anything we've ever seen before. One of the interesting things about robotics is that to some degree it's a copy of people and animals. And I think we all get used to thinking that it's easy to do the things a person does. For instance, I'm standing here and it takes no effort and it seems like nothing is going on. And I can walk across the stage, I can hold this object in my hand, I don't have to look at it, but I can manipulate it because I can feel it. I can look out at the audience and see all of you. I can count you, I can tell the men from the women. These are all amazing abilities that seem so easy. Yet in robots, it takes quite a lot of effort and development and patience and perseverance in order to do that. What are some of the things that are in the robots and in people and animals that make it able to do these things? One of the key functionalities is mobility, the ability to move around in the world, even when there's obstacles like stairways or rough terrain in the woods and things like that. There's dexterity, which I already demonstrated a little bit, the ability to pick up objects, to assemble them and fit them together. Really remarkable skill. There's perception, the ability to see the world around us, to feel the world around us, and use that. And then linking it all together is intelligence. You can sort of think of intelligence as a computing-like function. At least that's the model that's been used in recent years. Now, I believe that there's at least two kinds of intelligence. There's a cognitive intelligence and an athletic intelligence. Cognitive intelligence is like the thinking that goes on in our heads when we make a plan. Like each of you got to the meeting today, and I don't know where you came from, but let's say you were at home before the meeting, and you sat down and you thought, okay, the meeting starts at 1:40, that's what just started. It's going to take me 45 minutes to get here because there's always traffic in Seoul. So that means you can back that out and figure out when you have to leave. And maybe if it's not in rush hour, you'll use a different amount of time. But you can make plans, you can reason, you can solve problems, you can even just understand me talking up here using a kind of cognitive intelligence. But there's another kind of intelligence that's tied closer to our bodies. It's what let us move with efficiency so we don't waste too much energy. It lets us use our limbs and our muscles so that we get the maximum strength and can get the highest performance for tasks given what our physical system is capable of. And it lets us also work in real time, taking data, visual data, and other kinds of data in order to maneuver through the world, avoiding obstacles. Or let's say you're playing a game like basketball or football or soccer. It lets you maneuver with respect to your opponents. And I think of all these things as being athletic intelligence. And mostly Boston Dynamics over recent years has focused on athletic intelligence. Even though most of us aren't athletes, we all have a great deal of athletic intelligence that we use almost all the time. Here's some demonstrations of athletic intelligence in animals and other people. It's really remarkable what an animal like a goat can do and how much their whole life depends on the ability of them to balance and grasp the environment. And here's an animal that can run very fast, hoping to catch a meal so it can stay alive. And even humans have great amounts. An ordinary human or a very skilled, advanced human can do things that are just totally remarkable. And here's some crazy humans who are using their athletic skills in a very dramatic way. I assume that some of you were out this morning on all the apartment buildings getting a workout like this as well. Can you believe it? And even in this 2-year-old, now of course this is my grandson, so he's a very smart, special 2-year-old. But look at the skill he uses in coordinating his vision system and the motion of his limbs to figure out how to traverse this rough terrain. It's really remarkable. Well, at Boston Dynamics, for about 15 years, we've been building robots that have some amounts of athletic ability. This is way back in the early days of our work, where we're demonstrating that the robots are actively balancing themselves. And when there's a disturbance to the robot, it can adjust how it uses its limbs. It can calculate where it needs to place its limbs or how it has to move in order to recover from that disturbance. This is some slippery pavement in our parking lot. And then we went on to use what we learned in building Big Dog to make a number of other robots. Here's a large robot that can carry about 400 pounds, and it can travel both through the woods, like this bushwhacking, or obviously we come from Boston where there's a lot of snow in the winter, and it can also travel in terrain that's slippery and sticky and is an obstacle for most wheeled things. And this is the fastest legged robot in the world, about 20 miles an hour. And you can imagine all the calculation that has to get on in order to stabilize this motion, this robot, as it runs. So that's a little bit of the history of what we've been doing. And now I'm going to talk about the robots that we're building and selling today. A robot that is not quite ready to be sold, but will be in a year or two. That's tomorrow. That's the stretch robot. And then we're doing research on robots that aren't really products yet, but they'll be products sometime in the future. Or at least they're tools for learning about the problem of how robotics works. So I'm going to start with today. Spot is a robot that we have made, designed, and built that we are selling today. And the basic design of Spot, it's a small 4-legged robot. It weighs about 65 pounds. I know I should know what that is in kilos, but I'm sorry I don't. And we've designed it specifically to be a platform, which means that you can add hardware components and software components that are suited to your particular need and application. And on the right there's some pictures of an arm, an extra computer, some cameras that have various characteristics, a LiDAR, and some of our customers have put all different kinds of sensors on the robot. Now we've brought a Spot here that we're going to demonstrate. It's over on the side of the room there. And Seth Davis is our chief robot wrangler, and he's operating it remotely. So the robot has onboard computers that are controlling the motion of its limbs, that are taking data from its cameras so that it can avoid obstacles. You notice it's not running into any of you or your tables. And although Seth is driving it, he's only giving it very simple high-level instructions in order to do that. Now you notice that Spot came up the stairs, and I'll talk about that in a second. So as a 4-legged robot, if you think of 4-legged animals, they can use their legs in different ways. They can trot, which is what the robot's doing here, diagonal legs synchronized. They can walk. Here only one leg is being used at a time, picked up and moved forward, and then another one, another one. Are you going to do jogging or something? Here's a very slow walk. The slow walk allows it to carry the most weight because all the legs are on the ground as long as possible. And the robot can run, where it's using energetics and balance and prediction in order to control its motion. One of the cool things about a legged robot is it's omnidirectional. It can go sideways, it can go forwards and backwards, and it can also turn in place, as it's doing here. Now, as I said before, this robot has cameras. It has 2 sets of cameras in the front, which are both stereo and another set of cameras. And then there's one on the side, and one in the back, and one on this side. So that means it can see obstacles in all directions. Here, I'm going to be an obstacle. And Seth is just telling it to go forward, but when it sees me, it goes around because it doesn't want to bump into me. And I think he's going to do, are you going to do it again? And if you watch, you can see he's not touching the controls. The robot's just doing this on its own. But it can also use that kind of vision and control in order to do obstacles. You already saw it through the stairs, but we have some blocks up there, which it'll climb over. Since it has cameras on the side and the back, it can also go over obstacles sideways or backwards. And you notice the front legs didn't really need to climb there, so it kept them on the ground. So, you know, there's a computer in here. There's actually a bunch of computers in here and a battery and a bunch of other things in the hardware that all make it possible for the robot to think about all the low-level athletic intelligence. So all Seth has to do is give high-level instructions like go that way or turn or whatever it is. Now this robot also has, it can also change the attitude of the body. I forgot to say that. And that's really important because the robot has an arm, and Seth is going to open the arm up. And the motion of the arm is determined by both the arm and the body. And so we've done a lot of work to coordinate the programming of the arm and the body so that we can just think about what's the hand doing. So he's going to hold the hand in still. We call this chicken head mode. And now the body can move. And the hand stays still. And if you think about doing a task like grasping your water, you really want to be able to grasp it no matter how your body's moving. It can even walk while it keeps its hand still. And so we think this is really a key function of athletic intelligence for mobile manipulation. Anything else? Thank you, Seth. Thank you, Spot. Now, I'm going to talk about some of the practical applications of Spot that are going on around the world. We have a couple of spots in Chernobyl, which, as many of you know, it was the site of a nuclear disaster many years ago. And they want to do radiation measurements in places where you'd rather not send people. So we've outfitted Spot with a radiation detector and some specialized cameras. You notice it's wearing plastic booties so that they can decontaminate it. But we've also sent it to many different industrial types of facilities in order to use it to measure gauges, check for the safety of operations. This is on an oil rig in the Gulf of Mexico, British Petroleum. And it's the special mobility characteristics of Spot that make it so good for these tasks. Here, Spot's equipped with both a LiDAR and a specialized set of cameras, so it can go into this facility and go and do safety checks in many locations. This is another British Petroleum facility, which has to be patrolled. Here it's holding a methane sensor, so it's checking for methane gas leaks and also checking the status of gauges and dials. And again, it's the special mobility of Spot that makes it the unique solution that can do this. We've also been applying it for testing at electric power utilities where there are areas that you are not allowed to send a human while they're powered up. And in some cases, we've saved the operators large amounts of money because they can send the robot in to do a check without powering down the whole facility. Another application is in construction, where you'd like to build a digital model or a digital twin of a facility during the time it's being built. And although you can send a person around with a camera or sensors to do that, it's much more effective to have a robot that can be localized exactly in terms of the space it's in. We've also lately been programming Spot to do some dancing, and some of you may recognize your compatriots, the BTS. and they've been having some fun. We've all been having some fun working with them. We have several hundred spots around the world in various kinds of applications, all B2B applications of the kind that I just showed you in the video, but really, a more diverse set than that. And it's very exciting to see the crazy things people think of that they can use the robot for, and some of the very practical things. So that's today, a robot that we're building and shipping today. We have another robot that we're planning to use in the next couple of years to make into a product for the next couple of years. And it's aimed at a different kind of task, a very specific task, which is to handle cases. That's boxes of product. And it turns out that there's about 500 billion, 500 billion boxes like these handled around the world every year. And it's almost all done by humans, really backbreaking labor. And we've been developing Stretch in order to do some of the tasks in handling cases that are needed for warehouse and e-commerce and things like that. On the left, there's a picture of a truck that's floor-loaded with cases, and we've been concentrating on using Stretch in order to unpack the boxes from a truck. And this happens hundreds of thousands of times every day around the world. So we built some mobility. All of our robots have some specialized mobility. This robot has a visual system that can look at a stack of boxes and identify each one. I'll show you a little clip that shows what it sees. And here it goes and empties the truck one box at a time at a very good speed. Here you can get a visualization of what the robot's thinking while it does a task like this. On the right are the segmentation of the boxes in the image it just took, and it takes a new picture every time it has to grasp. And here in our, this is actually in our lab, we have 2 trucks that we're unloading simultaneously. Another task for a robot like this is called palletizing and depalletizing. So on the left, we're taking apart a pallet of product, and on the right, we're building another pallet. So that's depalletizing on the left and palletizing on the right. And it uses all the same hardware and skill components, but it gets a higher level program that works a different way. This is a prototype. It's sort of a second generation prototype, and we're very close to having a more productized design that can operate for many hours at a time doing these kinds of tasks in warehouses. So that's a thing that'll be coming to you before too long. Finally, I want to talk about Atlas. Atlas is we think of as beyond, or the future. It's really an R&D robot. We don't have any plans to make an Atlas-like product, but we use it to study the problems of mobility, dexterity, perception, and in a very complex situation because the robot has so many degrees of freedom, it's always balancing. And also, it's more like a human than our other robots. So I'm sure you've probably seen on the internet some video of Atlas, and most of what I'm showing you can get in various clips on the internet. So here, the robot has onboard computers that are used to control the motion of the limbs to perform these balancing tasks. Of course, it has sensors like a gyroscope that lets it understand how it's moving in space, even when it's not in contact with the ground. But it's also got sensors in the legs that let it measure loads and things like that. Now in this clip, the robot's using computer vision in very fast real time in order to help it to adjust to its own motion with respect to these obstacles and affordances. This robot has clearly gotten more athletic than me, both as I've gotten older and it's gotten more developed. And it's very exciting to see, and we expect to make more and more athletic versions of a robot like this as time goes on. Here's a first attempt to use the arms for mobility where it did a vault. So I want to make a comment about how you achieve AI for a robot like Atlas. I think many people think that software is responsible for all the intelligence of a robot. And in fact, software is really important. It's as important as something can be. And here we show some of the things that the software is doing. It's coming up with ways to do these maneuvers that are in the top row, like spinning in place or jumping up onto an obstacle or off it, or doing a stepping where it turns. All these things are things that software plays a key role in programming, taking the dynamics of the robot and its environment into account. In the lower left shows a little bit of the perception going on that I described earlier. And then it's also used to pull it all together in order to make behavior. But the point I want to make is that hardware, advanced hardware, is just as important for making advanced robots and making them have athletic intelligence. It's important to get robots that are light and strong and have wide range of motion. And we've been working really hard, partly with using 3D printing. So if you look in the lower right, that's the picture of a manifold that lets us put many of the physical features of the robot in one lightweight object rather than having hoses and connectors and filters which all build up the weight of the robot. We've also made a hydraulic power unit that's really compact. 5 kilograms produces 5 kilowatts of power. And we've done work on valves and batteries and all the other components. So I think combining work on the development of hardware for advanced robots is just as important as developing the software, although the software is key as well. And in fact, the software plays a role in designing the hardware. You know, once you do 3D printing, you need to be able to give a model of the object you want to build. You may want to optimize the behavior of that model, which you can do in software before you build the component. And so the two really feed back into each other. You know, using these techniques, we started with a humanoid robot that weighed about 170 kilograms. You know, that's a very heavy robot, and it was big. And we made it down to a proper size, about my size, and almost my weight. It's a little bit heavier, although there was an earlier version that was about the same as me at 75 kilograms. Well, I started out the talk by mentioning athletic intelligence and cognitive intelligence. And most of the things I've shown you really fit into the athletic intelligence sphere. And I just want to make the statement that I believe in the future, bringing cognitive intelligence into tight interaction with athletic intelligence is going to be the step to the next level of robot functionality. So for instance, wouldn't it be great if you, instead of having a team of expert programmers program the robot to do a task, you could show the robot a human performing the task. And then the robot could watch and understand and then be able to do it themselves. Now that's very difficult, and no one can do it today, and it's probably going to take many years before we can do that. But I think that's a direction, the kind of direction that we should go. I have one example of, that's my grandson again, about 2 years old, using his cognitive intelligence. He wanted to get all his toys from one side of the room to the other, and he could have gone back and forth, but he thought he could simplify it by doing this very sophisticated grasp where he couldn't fit all the parts in his hand, but he reasoned that he could hold them against his chest. I don't know how he figured that out. We didn't show it to him, but somehow human cognitive intelligence can figure things like that out. And then he took his toys and he played with them. Well, there's going to be many, many tasks like this, and I look forward to coming back and showing you how cognitive intelligence works with athletic intelligence in the future. So thank you.